is dx0 d tau, dx1 d tau, dx2 d tau, dx3 d tau. Now, we know that d tau is the proper time, so the proper time is the time. Right? Test particle has a certain mass, but that mass is very, 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 very small compared to everything else. It's so small that it doesn't cause any gravitational effect relative to the problem that we're studying. So that's its mass is very, very tiny. So you've got a mass that's small. You've got a clock by it. Oh, and it's right? That would be a CT here, so this would end up being C. This would be an alternative use. This would be dCt dt. So that's how you may have seen it in your special relativity coursework. So you end up with a factor of C, but in our case, C is 1, and then we don't have to deal with that. One of the nice reasons of choosing the C equals 1 set of units. So we end up with gamma V1, gamma V2, gamma V3, like that. That is our forward velocity. I'll put a little vector up there. That's our forward velocity for a basically particle, right? You give me V1, V2, and V3, I give you a forward velocity. So anywhere in this whole line, specify V1, V2, V3, and you end up with this forward velocity. And the is V squared. And anytime you exist, you end up with this is a beta instead of a V. And beta is defined as V over C. So if your units are not C equals 1, then you just take the ratio of V to C and beta, and you end up with 1 over the square root of 1 minus beta squared. But our unit C is 1, so we don't have to bother with that process, right? I'm just saying this because different people come from special relativity with different formats, right? So we just go with this expression for gamma. And V is the square root of V1 squared plus V2 squared plus V3 squared, right? This is where exponents and subscripts get confusing. So this is the definition of our forward velocity. But let's work this out a little bit. What is the magnitude of the forward velocity? The magnitude of the forward velocity is the magnitude of V nu, like that, which is going to be eta, alpha, beta, V alpha, V beta, right? This is our special relativity Minkowski metric, which we're always going to use as minus 1, 1, 1, 1. Right? That's our choice. Our choice of the Minkowski metric is minus 1, 1, 1. That's the flat space-time metric of special relativity. And so when we do this calculation, we will get, negative gamma squared, right? It's already magnitude, right? So it's negative gamma squared plus gamma squared V1 squared plus gamma squared V2 squared plus gamma squared V3 squared, which is going to equal minus gamma squared, gamma squared 1 minus V1 squared plus V2, oops, I'm going up space, plus V2 squared plus V3 squared, right? And that's going to equal, gamma, there's a minus 1, that's a minus 1 right there, right? It's going to be gamma squared over, or gamma squared, and it's going to be basically V, the magnitude of the velocity, minus 1. And, well, what is gamma? So let me bring it up here. But gamma squared is 1 over 1 minus V squared, and then the numerator of this thing is V squared minus 1, V squared minus 1 is the numerator. So that whole thing equals negative 1, but we're taking the magnitude, right? So it equals 1, which of course is the speed of light, right? The speed of light is 1 in our units. The point is that the magnitude of an an arbitrary velocity, of an arbitrary full velocity, is always c, right? Which is what I was saying. You just sitting still are traveling at the speed of light. If you're sitting still, you've got gamma 0, 0, 0 is your full velocity, but the magnitude of your spatial velocity is 0, so gamma equals 1, and the magnitude of this thing is going to be 1. So you're traveling at the speed of light all the time. And that's the thing you got to think about. Nothing is stationary in general relativity. Nothing sits still. It's impossible to be motionless. You can talk about being motionless relative to something, I suppose, but as far as any form of space-time measurement, meaning you have any kind of coordinate system, everything is moving in that coordinate system along a world line. Nothing is stationary. And furthermore, what's even more interesting is that no matter what world line you're on, you're always traveling at the speed of light. You're always traveling at c, or in our units of 1. And so let's put that idea that nothing is stationary in this business. And so that's an important way to start to think about general relativity, because we're going to think of these world line constructions. And we're going to squeeze these dimensions down into 2. There are problems that I'd love to be able to have on curved black holes where you can't really do it. You can't really squeeze everything down into 2 dimensions. So then you have to kind of imagine, how do you picture something in 3 dimensions? Like, if we have a chunk of space, right? If we have a chunk of space, how do you imagine this chunk of space? As a time dimension. I've seen people try different things. I've seen people try coloring, right? They'll start with blue, and then as it goes on, it'll turn. As time marches on, the line kind of changes color. All right. I've seen people try to do it where shrinking. Shrinking is what? You're imagining this cube. This is the cube at one time, right? And then you imagine at a later time, the cube is it's kind of shrinking. And that shrinkage is the time dimension, right? This actually looks like something people call a tesseract. This 4-dimensional cube. It's sort of got that 4 dimension. This is really not worth the trouble. I don't think it's worth your trouble trying to imagine that 4th dimension. But there's a lot of times where something like that might be useful. But for now, we're okay, because we're going to be able to squeeze our 4 time dimensions into 2 space dimensions and then 1 time dimension. So we're not going to have too much trouble with that. All right, so this world line concept, that's one big important thing I want you to think about. So the next thing is sort of one of these fundamental postulates ideas is that we're going to be talking about, let's imagine we have this world line, right? I'll stick to my sort of orbiting, I'm not even sure that that's a really good orbit. I think an orbit is better understood like this, right? We have this sort of orbiting object in our space-time, right? And there it is, that's its world line. There's coordinates on this space-time. Remember how we drew in the what is a tensor series? We drew coordinates like this, and I said, call that x0 and x1. And the very fact that you can do that, right? The very fact that this is possible, if I say this is symbolically representing space-time S, I can actually go into space-time and draw coordinates on space-time. And the fact that that's possible, right, that I can put 4 coordinates on space-time, that means that space-time is a manifold. And that is kind of an assumption of our mathematical structure of the theory. We're assuming that we can't lay down coordinates on space-time, and that space-time is actually a manifold. And the 4 coordinates are x0, x1, x2, and x3. And this process can actually be done. Let me erase this guy for a second. The implication of this, of course, is since it's a manifold, we know that what we really have some R4 out there. And if this region of space-time is some chart, remember we were getting the charts U alpha was the name? Then this mapping from R4, which has this coordinate grid, that mapping is the inverse of the chart mapping, laying down these coordinates into space-time. So when I draw this thing, and I say, okay, here's our x0, and here's our x1, and here's our x2 axis, this thing here is meant to be this. It's meant to be space-time with coordinate lines laid down through this inverse mapping from some R4. That's what this is. This here is space-time, and these lines I've drawn here are supposed to be this thing I've been symbolically talking about in the manifold lectures. So this is actually like a realization, an instance of this. And so there's some other R4 out here. There's some other R4 out here that's mapping into this region with some kind of inverse mapping. And laying down these coordinate lines are like this. And then, so the x0 coordinate lines, x2 coordinate lines, and it's chopping up and dividing up and it's slicing up space-time. So space-time is a manifold. And therefore, if space-time is a manifold, we have kind of all of those tools that we were talking about before, right? If I'm now going to say, this is a path through space-time, well, it's a path. It's a curve. Well, what's a curve? A curve in a manifold, since space-time is a manifold. I'm not even going to draw the coordinates. I'll do this. I'll draw these little coordinates, right? x1, x2, x0. The time-like coordinate will always be 0. We'll discuss what distinguishes a time-like coordinate from a space-time coordinate a little later. But if this is a curve, and here's our space-time manifold, and here's a path in space-time, and there's a test particle that's following this path, presumably. In other words, this path is modeling the motion of a test particle in general relativity. Well, what does this mean from our manifold perspective? Well, I have some interval on R1, and I have a beta, and I have a map from that parameter into space-time. That map is going to be called x alpha. I'll put the parameter in there as beta. It's a function of beta. So for every value of beta, I can create a point in the manifold whose coordinate is x alpha. And as beta moves from 0 to 1, this test particle moves from x alpha x0 ultimately to x alpha x1. And every value of beta is mapping will now drop the location of the coordinates of this test particle at all these different points. So this might be x alpha 5, right? For example. And when I look at x alpha, of course, I'm thinking of x0, 0.5, x1, 0.5, x2, 0.5, and x3, 0.5. Right? And that is how we understand the path in space-time. It is parameterized as a curve on a manifold. And that tells us quite a lot, right? I mean, once we have a curve in space-time, we can now talk about tangent vectors on that curve, just like we have in the previous lesson. Lessons about tangent vectors. And we can also talk about the length of this curve. And we're going to do that. We're going to talk about the length of this curve in space-time. But the point I'm trying to get now is, before we go into those specifics, is that space-time is a manifold. And that's basically an assumption of the theory, right? The theory leans on that mathematics of being a manifold. And so now this is some confusion here, I think. And I'm not sure I've ever really resolved it myself, but understanding that if space-time is a manifold, right? Here's our manifold of space-time. Remember, manifold requires that, okay, this region has a chart to R4, and every region has a chart to R4 if we are dealing with a four-dimensional manifold. Now notice that says nothing about the metric, right? Being a manifold does not tell you anything about the metric. Sometimes you'll see people say that because space-time is a manifold, every little region of space-time locally must look like a Lorentzian flat space-time. And that's not every local piece of space-time looks Lorentzian. That's the last point we made in this first lesson. But all this says is that every region of a manifold has to have coordinates in four dimensions. Now, in addition to that, it turns out that there's another assumption of the theory that does get you as far. We'll talk about that. But just because it is a manifold doesn't mean anything about the metric. All it means is that you can lay down coordinates, and it's a differentiable manifold, right? In the sense that the transition functions are all differentiable functions, just like we learned about in the what is a manifold function. So the key assumption that we're dealing with, though, is that space-time is a four-dimensional manifold. Now, on top of that, then there's the first principle that's actually really important, and we'll cover that as our last subject for today. And today it's called the Einstein equivalence principle, the EEP. And the EEP is usually, I think, we'll talk about because it's kind of like the way it's presented in books when I learned about it, because the presentation doesn't get you to sort of the mathematical modeling of it. But the typical presentation is this guy in an elevator. And I mean, it makes a lot of sense. I totally get it. That, you have a guy in an elevator, and he's basically, the elevator's in open space. It shouldn't be an elevator, just say a guy in a box, right? And he's just floating in open space. There's no gravity, there's no earth, there's nothing. He's just floating there. And if you start accelerating the block very smoothly, and it's like sometimes we'll put a little rocket engine on it, saying that this rocket engine is providing a constant force, metered very carefully so that the acceleration is constant, right? And so once he does that, then the guy is no longer floating. He's now standing in the elevator. As long as this acceleration is constant, and let's actually say this acceleration of gravity is 1g of acceleration, that this is indistinguishable. There's no experiment that can be performed inside this little box that distinguishes it from the situation of a guy standing in a box on the surface of the Earth, right? But this is the Earth, right? And the Einstein equivalence principle basically is various versions of this moving rocket elevator situation that covers a variety of different situations. And the key one of this, so this one here, this particular thought experiment shows that uniform acceleration is indistinguishable from a gravitational field locally, meaning that this box is small enough, and we'll talk about it being big enough in a moment. But it also means that a person floating in free space, in absolutely empty space, right? Little guy in a box in free empty space, that is indistinguishable from, or a guy in a box moving with uniform velocity v. How about that? A guy floating in a box using uniform velocity v, he can't be distinguished from a guy freely falling in a gravitational field. So a guy who's freely falling under the influence of gravity has no way of knowing if he's not in a box just moving along, if he's not in a box where there is or isn't any gravity. He can't detect. There's nothing that he can do to detect the existence of the local presence of the Earth accelerating him, short of a non-local experiment. For example, if he looked out the window and looked at the Earth and saw it there, or shown a laser beam of the Earth and reflected it back, and kept track of his relative motion with the Earth, he could do that. But that's non-local, right? That's non-local. Locally, that means inside this little box, there's really no experiment he could perform to decide if he was in a gravity field, or if he was just floating out in space. So the question is what is local? What is local? And this is a pretty important question, because you can certainly imagine this circumstance, right, where here's the Earth. I'll just think of from the Earth. Here's a large massive object that's clearly gravitating, a very dense massive object. And there's two. That's a very kind of standard picture, by the way. There's two test particles that are falling, and we know they're going to fall towards the center of the object. And what's evident by this picture is that the distance between these two test particles, right, it gets smaller because they're both going to the same spot. So, in principle, if the box that I was talking about, the lab that was covering this, was this big, you clearly will sit in the lab, and as the lab falls, and the balls fall, you will see the balls get closer and closer together. It'd be like sitting in a lab looking at two balls that just tended to come together, right? They're actually, the distance between them, it's like they're attracting each other. Right? That's what it'll look like to you. It'll look like to you as though those two balls are attracting each other. That's what it'll look like to this guy right here who's with the lab. He'll think these balls are just attracting each other. And clearly, once he sees that, he'll recognize, wait a minute, I must be in this circumstance. I must be in this circumstance, and therefore I'm in a gravitational field. So there's an experiment he could do to determine that he was in a gravitational field. If he was not in a gravitational field, if he was just floating way out in space, then these two balls would just sit there in the lab far apart from each other, and he wouldn't notice any change. But because he sees these balls coming together, he knows he's in a gravitational field. So we can't have that. So what do? Well, we shrink the lab. But obviously, that problem, if you shrink the lab, that doesn't really change anything, right? The balls are still going to, starting in two different places, they're still going to the same place. They're still going to get closer together. So as long as you can detect it, you can shrink the lab more and more and more until you can no longer detect it. And it really has to do with the quality of your measuring device, right? If you have a measuring device that is so precise that it can take two balls 1 centimeter apart, and an Earth that's 1,000 miles away, right? 1,000 miles away, say 1,000,000 miles away, right? Really far away. If you're so good that you can detect the slight drift of these balls together due to the tidal forces in that situation, well then, you're not local, right? Local is sort of this relative to, it's always local relative to your ability to measure. And the higher your precision of measuring, the more, the smaller your lab has to be. Right? So if this situation is too big, you've got to just get smaller. So the point is about this is that we nature will always be your measuring equipment, right? There's no level at which your measuring equipment is so precise that that nature, you can't imagine a smaller lab. It's a limiting process. It's an epsilon delta type limiting process. You set up how precise your ability to measure is, and nature will find an epsilon laboratory size that will be your measuring apparatus. That's just the way it is. Meister Wheeler talks a lot about this, and it's pretty interesting. All you need to know is that local just means small enough that you can't detect this very process. You cannot detect this process. So, very well, but how does this implicate the theory, right? So we're going to go back to our notion of world lines, and we're going to talk about, we were talking about world lines, but now imagine a free falling object in space-time, and I like to draw like this, I always think of orbits, right? So here's an object just orbiting a star, and it's in free fall, right? It's in free fall. And free fall just simply means there's no other forces, there's no forces at all acting on it, right? Not even, because gravity, we're not calling a force, right? Gravity is going to be this following of the geodesic trail in space-time, a little foreshadowing, but a force would be an electromagnetic force, right? An electromagnetic force of some kind, or failing electromagnetic force, perhaps the strong force or the weak force, right? So if it's none of those forces, then if there's none of those forces are at play, the particle is free falling. And it still could be accelerating, of course, because of gravity, but these forces are not acting on the particle at all. So the particle is free falling, and its path through space-time is given by x alpha of some parameter, and I'll call that parameter tau for now. In our next lecture, we'll see why tau is going to be the proper time. But that is what this path is. It's x alpha, and tau being the parameter, of course, that's just our one, right? Defining a curve, and so tau is the parameter. And the point is that we're allowed to make coordinate transformations, right? We talked a lot about coordinate transformations when we talked about tensors. What is a tensor and how tensors change in the coordinate transformations, and namely, the essence of a tensor doesn't change. But what the free falling particle, the way this Einstein equivalent principle, all of this elevator stuff, the way it translates to our world line understanding is it means no matter what world line you're on, as long as it's free falling, no matter what free falling world line you're on, you can always do a coordinate transformation so that your coordinates at that point on the world line, that coordinates is Minkowski. They're Minkowski coordinates. Minkowski coordinates. Right? You can always find a coordinate transformation that will place the coordinate system of special relativity at your spot. And the coordinate system will be free falling coordinates. They will be coordinates that are associated with your falling motion. And we'll call geodesic coordinates. And you can also geodesic coordinates as well. How to about geodesic coordinates. The Einstein equivalence principle is this assumption. It's this statement that anywhere on a free falling world line, you can take this coordinate system and say, I'm going to put up a coordinate system right here at that particle, or I'm going to establish a coordinate system such that at this point we have Minkowski space-time. And what that means is not only do you have 4 dimensions of coordinates, but you also have a metric at that point. That metric at that point is equal to minus 1, 1, 1, 1 diagonal. The diagonal of that. Right? That is the metric there. So we know that the metric tensor will exist everywhere on the manifold because the metric tensor is a tensor field. But whatever that metric tensor field is, at this point, its value is equal to this. So the way to think about that in terms of the work we've done in the previous lecture is we have our space-time coordinates, right? We know we have a metric tensor field, right? It's a function of space-time. So now we know that at every single point in space-time, you can create a new set of coordinates, a new coordinate transformation that will take that at that particular point, say that point's P, G, A, alpha, beta at point P is going to equal. It's going to be G00 equals negative 1, G11 equals 1, G22 equals 1, G33 equals 1, and the rest are 0. So I can always find a coordinate transformation such that this is true at the point P. And in fact, we can even go a little bit farther, and we can say we can always find a coordinate transformation such that this is true at the point P, and furthermore, G alpha beta with a derivative with respect to space, or with respect to the coordinates. So I'll say gamma, that equals 0. So all the first derivatives are 0 of the metric tensor components, and the metric tensor components equals the Minkowski metric components at each point in space-time. And that's what this means, right? This freely falling condition looks to you like absolutely flat space-time, right? There's nothing you can do to tell the difference. Therefore, you believe you are in the space-time of special relativity, and the metric of the space-time of special relativity is beta alpha beta minus 1, 1, 1, 1. Therefore, whatever coordinate system you were using before, or whatever coordinate system say he's using, you can find a coordinate system where you believe that the metric right at your calculation of the metric location is minus 1, 1, 1. His calculation will be different if he uses a different coordinate system. It's as simple as that. Now, the physics of everything is always going to be the same, because these coordinate changes don't mean anything. All the laws of nature must comply, or must be identical in every coordinate system, therefore they must all be tensorial. And that is yet another assumption, right? Is that the nature of general covariance, all the laws of nature must be the same. But the Einstein equivalence principle, that's this idea of the freely falling elevator being the same as the guy in regular inertial motion of special relativity, the uniformly accelerating elevator being identical to the earthbound elevator. All of these things, what they really mean is that we can make coordinate transformations that will take any point in the space-time. I illustrated it as points on these free-falling paths. I kind of say, okay, you're on a free-falling path through space-time. Well, at every point on that path, you should be able to make a translation coordinate change, so you feel like you're in Minkowski space, regular space of special relativity. But it's true for every point in space-time. At every point in space-time, you can create a free-falling coordinate system that looks exactly like Minkowski space. And therefore, that transformation exists from whatever coordinate system you're using to one that is absolutely flat, right in the immediate vicinity of that point. And exactly flat means this equals this, and this, and also the first derivatives are equal to 0. You can't get the second derivatives to be 0, by the way. You can only get the first derivatives to be 0. And of course, it's always an approximation. You can't say the second derivatives aren't 0, right? So, you are limited to being global for this coordinate system to have all this true. This metric will only equal its values at the point P, literally. So any deviation from P, they're not quite the same. So you have to shrink your lab to a point where you can't notice those differences in order to really sort of live through this kind of experiment. If you're going to try to experience that kind of experiment, you have to really shrink your lab down. Now, understand this by no switch to new coordinates. These are coordinates. And at the point P, in the new coordinate system, G alpha prime, beta prime, at the point P. Actually, what I'll do is instead of B, I'll say XP, right? So in this case, I'll say XP prime, right? So it's still at the same point. It's at the same point. But in the new coordinate system, right? dx alpha, dx beta, where this is all the new coordinate system, the value of this at that point is going to be negative 1, 1, 1, 1, and all the rest is 0. The diagonal, they like to say diagonal. Basically, we're reading the diagonal elements of this thing. I don't like thinking of the metric as a matrix. That's a real bad idea. So I'm just trying to say 0, 0, 1, 1, 2, 2, 3, 3. I'm saying G0, 0, G1, 1, G2, 2, and G3, 3. Equals minus 1, 1, equals 1, equals 1. I can always find a coordinate transformation that will make that happen for this point. And furthermore, I can make the derivatives of these guys with respect to the spatial coordinates. I can do G, alpha prime, beta prime, gamma prime, equals 0 for all those coordinates. The fact that that can be done, that, think about this, right? We're talking about the black coordinates. We're saying, okay, here's a manifold. We've got a metric. And I told you in the last lesson, we know these metrics can be arbitrary. Mathematically speaking, you can create all kinds of metrics. But the fact that I'm allowed to make a coordinate transformation so that every point will always have a metric of this type, that is a bit more of a constraining statement. I have to make sure that for every point I can make this coordinate transformation and shove my metric into this form. For example, and there's only a limited number of possible forms that a metric can be. There's not that many, right? You could be Euclidean where they're all plus signs, or you can imagine a minus. You can imagine a minus. You can imagine an extra minus sign, right? You can imagine two minuses, two plus signs, or something like that. But that's not the metric of special relativity. The metric of special relativity is one minus sign and three plus signs, or one plus sign and three minus signs. You can take the full negative, right? But it's not plus. That would be Euclidean. But either way, the Einstein equivalence principle is basically asserting that you can make that transformation for any point in space-time. It's kind of important. All right, so where this is all headed, and we'll start beginning it next lecture when we talk about GD6, is ideally our goal is to find out. Our first goal is to find out this function. I want to know, given a space-time, and when I say given a space-time, I mean given a metric. Given a metric. If I'm given a metric, and I have a test particle freely falling in space-time that has this metric, I want to know what is its path. And that is asking, how do I take this parameter from R1, map it into the manifold through this function, and I will get coordinates for each of these points. Right? And remember, those coordinates were laid down on the space-time because space-time is a manifold. Right? Space-time is a manifold. So that allows me to know there's coordinates here. I can find these coordinates, or I can establish the existence of these coordinates, and I know that there's a path, right? Because this is physics, right? There's definitely a path of the particle, and I can parameterize the path one way or another. And I'm going to actually parameterize it with the proper time of the particle eventually, as we'll see that next time. And my goal is to calculate this. Given this metric, calculate this path, calculate these functions. And we're going to do that for the metric of the Schwarzschild space-time. We're going to do this for the metric of surrounding a black hole or a very, very dense star. And it's going to start easy, but I'm going to push it as far as I can. But that to me is kind of the goal, right? I want to be able to calculate these functions. I want to know. You tell me what time it is according to this guy, and I'll tell you where it is. I'll tell you where he is. Now, it is interesting when I think about this. He tells me what time it is. The particle tells me what time it is. But now I've got my own clock, right? Because I've got a coordinate system that has a time coordinate and an x-coordinate. I have to define what that means. Coordinate time and proper time. Right? That's what this function is. It's the relationship between as proper time ticks, how is coordinate time ticks, coordinate time ticks slower or faster than proper time. And so that's the interesting one. The other ones are pretty easy. X1 is just, well, where are you on the X1 axis when the test particle's on the clock clicks its own number? Of course, I can also ask, where am I on the X1 axis when the lab clock clicks its own number? Right? So this might be more apropos to sort of a lab observer, a lab clock, and a lab location. So, but ultimately, if I have this, then I get this, and then I can calculate this without much trouble. So this is really it. If I can do all this, I'm really good shape. But in general relativity, what is important to understand is that the proper time is always going to be the time as ticked off by the clock of somebody floating through space-time. Whether they're free fall, whether they're in some kind of accelerated motion, doesn't matter. The clock building into the little test object, that oscillator and that counter, will always click the proper time. The coordinate time, however, in special relativity, the coordinate time was always the time of some sort of laboratory, right? You would have a laboratory that's sitting still, and they would say it's time t. this by taking derivatives of each of these terms with respect to tau, right? And so you have to do like d gamma d tau. It can be done. It's not totally tricky. It's just you got to keep track of things. But by the time you calculate this and you execute this, you're going to get a 0. And so no acceleration in the universe can change your pore velocity because all acceleration is forever orthogonal to pore velocity. So that's the way I want you to think about movement in general relativity. Always think about it in the context of moving through space-time.